Good day, sir.
Today, sir, we are Group 6 from BSCE-2B and we are here to discuss the Torricelli's theorem together with the sample problem that we'll discuss later. We will start our discussion together with Mr. Zantua.
I am John Elvino Zantua, the first presenter of Torricelli's theorem, and I'm going to present about the inventor of this theorem and brief context about Torricelli's theorem. Did you know that this theorem was invented or derived from the name of the inventor? And did you also know that this inventor or this author is not a woman but he's a boy? Did you also know that this inventor is not an architect nor an engineer but he's an Italian physicist and a scientist? This theorem also was invented in the late 1643, and this theorem has various aspects of application in physics. So let's move to the discussion about Torricelli's theorem. So what is Torricelli's theorem? According to this theorem, the velocity of the water that flows out of the hole to the ground due to the force of the gravity is equal to the velocity of the water through the height from the top of the liquid surface to the hole. Or in other words, in simple words, this physics law explains that the relationship of the water flowing out to the hole and the height of the liquid or the water in the container.
Good day, sir. I am Jorina H. Roberto, the second reporter for this group. About Torricelli's theorem. This theorem states that when a fluid moves, its total energy stays the same. It has three energies: the kinetic energy, the potential energy, and the gravitational energy. So when a fluid flows, these three energies stay constant. Whether the hole is high up, down low, or even sideways, as long as the fluid is moving, the total energy made up of kinetic, pressure, and gravitational energy will stay the same along the path. For instance, as you move down the slide, your speed, your kinetic energy, the pressure of the water in the slide, and the height, or the how high are you on the slide stays the same. So that your total slide experience will be good. Next reporter.
Hi, I am Maria Lorraine Silves and I am the third reporter of the group. So, Torricelli's law. So, loosely speaking, liquid at a greater depth in a container is under high pressure. Therefore, water flows from a hole in a tank at a higher speed V if the hole is at a lower depth edge. So, to explain this further, let's focus on the figure attached. So, the pressure of the liquid increases with the depth. So, kapag mas ilarom, mas increase ito yung pressure. So, kapag bubumuan tayo dito behind high pressure, which is area obus, if flow with water is madagmit, makusog. So, kapag bumuan tayo dito yung igbaw, which is low pressure, it flow with water is mahinay. So, nati ka igbaw it buho, nati ka hinay it flow with water. So, daily life examples of Torricelli's law. Filling a water bottle. The water flows out faster when the bottle is filled due to the increase in height and resulting increase in velocity. So, for example, alin water bottle. It high pressure din sa ade ka igbaw. Pero, pag igtip natin, pressure eventually matratransfer igbaw. So, that will result na mag-increase it speed, heat, water flow. Emptying a bathtub. So the water drains out faster when the drain is open due to increased velocity caused by the height of the water above the drainage. So, if drainage it bathtub is adding its surface kay it pressure, di ba? Kaya di ka obos. So, mas madagmit kapag it pressure adi ha obos kay it drainage adi obos. So So, mas madagmit itiya agos it water.
So, hello sir, I am the next reporter. I am Crystal Altares, and I will be discussing about the derivation of Torricelli's law. So, we are done about the explaining the concept of Torricelli's theorem. So now we are going to formulate a formula for this theorem. So let's begin. Let us assume that there is a hole in a liquid container consisting water in it at the depth of h from the top surface cylindrical container. Assume that the fluid is incompressible and that the opening is small relative to the size of the container. So in this situation, may data ko no container nga abrido lahiya. Tapos ito nga container bubuhoan ta ko no ito denoted that the height of the hole from the surface of the water is h. So to calculate the velocity of the water flowing out of the hole, so we must apply the equilibrium formula. We know that when we have a bottle full of water, there will be a potential energy. And then when we poke a hole in a container, there will be a gain of kinetic energy. Remember that potential energy is denoted by mass times gravity times height, while kinetic energy is denoted by 1/2 times mass times velocity squared. So to come up with, we'll have a equilibrium formula, which is, as you can see in the screen, there will be a potential energy loss and there will be a kinetic energy gain. So if we simplify the equation or the equilibrium, to find the velocity, we must both divide both sides by 1/2 times mass in order for us to cancel out and to remain the velocity squared. So therefore, we will come up with this equation. So we will have gravity times height time equals to 1/2 times velocity squared. And then in order for us to really find the value of the velocity, we must square both sides, and then we will have a equation which is velocity is equals to square root of 2 times grams times height. So, however, remember that this formula will be only used if the liquid in a container is an ideal fluid. And an ideal fluid is not compressible, has no friction, and the opening is small relative to the size of the container. So, dapat, itiya container, buhit na container, diri hiya madarada ko, hit opening, hit nga container. And then, ini nga formula, magagamit lang ni kung affected it, kumbaga, gravity is involved in the situation.
Good day, sir. I am Angel Desirepalda, and today I am going to discuss the derivation of Torricelli's theorem from Bernoulli's equation. Now, in order for me to discuss Torricelli's theorem, let's see this experimental setup. So, I have here a container in which it is filled with a fluid up to a height of y2. At a different height, which is y1, there is a hole in which the fluid flows out. The height from the distance from the hole up to the water surface is h, because the height is equals to y2 minus y1. And this cross-sectional area here is labeled as area 1, which has a velocity of v1, and this cross-sectional area here is labeled as area 2, which has a velocity of 2. Now, let's make an assumption that relates to the velocity that the water flow down.
So you can see here that we have a continuity equation. And if we assume that this cross-sectional area here, which is A2, is much larger than this cross-sectional area here, which is A1, we can see that the continuity equation here is V2 equals to A1 times V1 divided by A1. Magiging 0 here. Because area 2 is a large number, and a number divided by a large number has an answer that is closer to 0. So we assume that V2 is equals to 0. Now, the second statement that I will make is the pressure. Both of this section has a pressure. So outside the hole has a pressure 1, and this section here has a pressure 2. So both of this section is exposed to air. It is exposed to the atmosphere. So both pressure 1 and pressure 2 makes it atmospheric pressure and it has the same value. Now, pwede na kita tanan kuan. Makadto na kita ha, equation han Bernoullis. Para ma-derive naton ang Torricelli's. So ang equation nga niya adi na ya PPT. So ang pressure ngadtuhan na cross-sectional area cross-sectional is equals to P1 plus the kinetic energy is 1/2 times its density times its velocity 1 squared plus its kinetic potential. Its potential energy is density times gravity times its height 1. So ang pressure liwat nga tuhan hole is P2 plus its kinetic energy, which is 1/2 density times velocity 2 squared plus its potential energy, which is PGY2. Now, notice nga ganyakan ko kanina nga both pressure has the same value because atmospheric pressure na nga duwa. So, pwede natin i-cancel. Tapos, nagyakan ko kanina nga its velocity 2 is 0. So, the kinetic energy that's associated with this will become 0. So, mas 0 adi. Ay, dere. What I mean is, mas 0 ang nakadihan P and V2. So, pwede na ito ma-transpose adi, tikad to ha other side. So, 1/2 density V1 squared is equals to PGH squared minus GY11. Notice nga tanan nila by the density. Nga ng density nga ton container is constant. So, pwede na ito ma-cancel out. Ngan para ma-cancel out gapan to, times niya in both side, in 2. So, pwede na ito ma-cancel. So, it masasalin nala, pwede na yung G. Density times gravity times velocity times density y minus since both side nga nihi by the gravity pwede naton hiya ma-factor out. So it mangyayari masusugad. Tapos para ma-cancel natin its squared, pupuntahan natin yung square root. Notice gyap kanina nga, nagyakan ako nga, y2 minus y1 is equal to h. So, pwede natin niya ma-substitute. So, velocity is equals to gravity. By the ngayon ako ngayon to kanina nakalimutan ko la sir, in times ko ngayon hiya to. So, magbubutang kita ganihin to 2 times gravity gravitational constant times h. Since y2 minus y1 is H. So, ang ako na-derive from Bernoulli's theorem, tika diha Torricelli, amo na ini. So, let's go to the sample problem. So, next slide. So, pwede ko nga di problem number 1. Anayakan nga di, sir, suppose ko no, a tank with a cross-sectional area of 1 meter squared contains a spigot at the bottom of the tank with a cross-sectional area of 0.01 meter squared. If the spigot is 10 meters above the surface of the tank, calculate the velocity of the water leaving the spigot. So, ang iya given is, i-show na natin. I-show natin ang ka-drawing. So, nayakan ko, no, may container, tapos may nga this spigot has sides. Tapos nayakan ko, no, ang cross-sectional area ng tank is 1 meter squared. Ngayon, ang cross-sectional area ng spigot is 0.01 meter squared. Ang distance from the spigot up to the water surface is 10 meters. So, ang pakya na yan, ano ko na ang velocity? So, gagamitin ko na kanina, anak ko na-derive nga Torricelli's equation. So, V is equals to 2GH. So, maaram kita nga at gravitational constant is 9.81 meter per second squared. Nanayakan ko nung nga di ang height is 10 meters. So, if i-calculate natin ini, it magiging answer kay 14 meter per second. Amo ang iya velocity. So kanina, nagyakan ako kanina nga ang V2, ang velocity nga tun igbaw, ang cross-sectional area is, nag-assume kita kanina nga 0. So papatunayan ko yung nga 0 yan na. V2 is equals to, gagamitin natin ang continuity equation. A1 times B1 divided by A2. Nayakan, ang area 1 is 0.01 meter per second times 14 meter per second divided by 1 meter per second. If i-calculate natin ito yan magiging 0, V2 is equals to 0.14 meter per second. Hanapin na yan 0, sir. So, napatunayan ko, 0 talaga. So, na akong pag-assume, 0. Amo na. So, that's it for today. Oh, for my... So, thank you, sir.
Take over na yun.
So, nag-brown out. So, I am the next reporter. I am Geraldine Bisabinay, Bisabinay from BSCE-2B. So, I will be solving the next problem we have here, the next sample problem. But first, let me again explain what is Torricelli's law. So, Torricelli's law means or explains the relationship between the fluid coming out or flowing out from the spout or the hole of the container and the fluid inside the container, the height of fluid inside the container. So, let's proceed to the sample problem. So, we have here a problem which is a construction site where a water storage tank designed by a civil engineer is filled with water to a depth of 15 meters. A specialized spout located 10 meters above the tank's bottom is incorporated into the design. To assess the hydraulic characteristics of this system, the following questions arise. So first will be determining the velocity at which water will emerge from the spout when it is opened. And next, we will be calculating the horizontal distance from the base of the large tank where the water lands after exiting the spout. This information is crucial for ensuring the safety and efficiency of the water discharge system in the construction setting. So first will be determining the velocity at which water will emerge. And the velocity in water. So, drawing tayo na. So we have a container and may spout yan. And height ko naman spout, tikang surface. Sir, sorry, ayam. May nakita di height. Tikang bottom container up to spout, which is 10 meters. And may nakita liquid. Tikang di liquid. At water level inside the container up to the bottom of the container is 15 meter. And our given is i-label tayo nga 10 meters, which is our Y1, and our 15 meters is label tas Y2. So our given, so ang malito natin given, aton Y1 is 10 meters, aton Y2 is 15 meters. So again, kanina na-discuss mo ni Angel ang pagbilihan height, which is height equals to Y sub 2 minus Y sub 1. Aton Y sub 2 is 15 meters, and aton Y sub 1 is 10 meters. So aton height is 5 meters. So may rin nakita height. So let's proceed to the solution. So in this problem, we'll be determining the velocity of the water. So we will use the Torricelli's formula, which is already discussed by Angel, to derive from the Bernoulli's equation so we get the formula of Torricelli's. So we will be using the Torricelli's formula. So we have to. We will be substituting our given here in the formula. So our gravity is 9.81 meter per second squared, and we already calculate the height, which is 5 meters. And we will just be calculating. Five. So our velocity is 9.90 meter per second. So the velocity of the water is 9.90 meter per second. So here is the solution, here in the slide. So we have here 9.90 meter per second. So that's all po.
So, good day, sir. I'm Ramos Will for Alexandre Insay. We deeply apologize for the loss of power. The PowerPoint that didn't show from the starting of the losing of the power will be shown through the video after this presentation. Now, I will move on to the presentation of Ms. Sabinay, which is continuing his presentation. It may not be applicable for you to see the PowerPoint. Later on, I will make an effort to show you the PPT after this presentation. So, continuing Ms. Sabinay's solving, next is we will have to calculate the horizontal distance from the base of the large tank where the water lands after exiting the spout. This information is crucial for ensuring the safety and efficiency of the water discharge system in the construction setting. So, so I will show sir the free body diagram. Since Miss Sabina already found the velocity, which is the 9.90 meter per second, now I will have to find the time. So, using the vertical projectile motion formula, we will now have to evaluate the solution. So this will be cancelled since it is 0. So using the vertical projectile motion formula, I evaluate the formula using the solution. Change of y is equals to 1/2 gravity times time squared, and then 10 meters is equals to 1/2 quantity of 9.8 meter per second squared times time squared. So we can evaluate this answer by calculating this solution. So the answer will be 1.43 seconds. Now that we have already found the time, we have to find the meters. I mean, we have to find the x distance. Erase. So using the horizontal projectile motion formula, we can now evaluate the solution. So this will be cancelled since it is 0 again. So, using the horizontal vertical motion formula, I can now evaluate using the formula into a solution the 9.9 meter per second, which is from Miss Sabinay, and 1.43 seconds from the time. So, using the calculator, we can now evaluate this solution into the final answer, which is 14.1 meters. So that will be all. Thank you so much, sir, for the understanding. We apologize for the sudden loss of power. The PPT that hasn't shown with the screen will be shown later on after this presentation so that it will be applicable to you to understand what we have discussed since the power has lost. And we are the group 6 from BSCE-2B. Thank you so much, and we apologize again.
Thank you,
Thank you, sir.
Thank you.